Hi everyone, I will be doing a walkthrough for the discussion for worksheet. The first question we have here is about utilities. And looking at the first question, our utility function is 2x. And so if you want to find the utility of a single value, then you just plug that value into the function. So for part A, you just get utility of 3 would be equal to 2 times 3, which is 6. And for B, we are finding the utility of a lottery. And when you find the utility of a lottery, you want to apply the utility function before you've taken the weighted average. So do utility of 2/3 this lottery equal to 2/3 times the utility of 3 plus 1/3 times the utility of 6, which is equal to 2/3 times 6 plus 1/3 times 12, which is equal to 8. And for C, you do the same as what you did in part A, and you get minus 2, or 2 times minus 2, which is equal to minus 4. And for part D, you combine what you did in parts B and the previous ones. So you do the utility of that lottery is equal to 1/2 times the utility of 2 plus 1/2 times the utility of this lottery, which is 1/2 times 4 plus 1/2 times the quantity of 1/2 times 8 plus 1/2 times 12, which is equal to 2 plus 1/2 times 4 plus 6, which in this case is equal to 2 plus 5 is equal to 7. Now, moving on to number 2, you basically do the same thing, but you just have a different utility function, which is x squared. So the utility of 3 is equal to 3 squared, which is 9. The utility of this lottery is equal to 2/3 times 3 squared plus 1/3 times 6 squared, which is equal to 2/3 times 9 plus 1/3 times 36, which is equal to 6 plus 12 is 18. And the utility of minus 2 is equal to 4. And the utility of this lottery is the same thing that we did in part D of the previous question, of the same process, which is 1/2 times 2 squared plus 1/2 times quantity of 1/2 times 4 squared plus 1/2 times 6 squared, where this is the utility of that inner lottery. And we can simplify this down, so we get 2 plus 1/2 times 8 plus 18, which is equal to 2 plus 13, which is equal to 15. Okay, moving on to number 3. What is the expected monetary value of the lottery? And this can just simply be done by just calculating the expected money you'll get from this lottery, which is 2/3 times $3 plus 1/3 times $6, which is equal to $4. Okay. For number 4, for each of the following types of utility functions, state how the utility of the lottery compares to the utility of the amount of money equal to the EMV of the lottery. So part A will be a question mark, which will be more clear as we go on to parts B, C, and D, mainly because we don't really know the characteristics of the function, so we can't really say anything about that comparison. So for part B, if U is monotonically increasing and its rate of increase is increasing, then how do those two values compare? So an example of a function that is described in B would be x squared. And you can see how it's an increasing function and its rate of increase is also increasing. this corresponds to utility functions that are more risk-prone. And in the case of risk-prone functions, they prefer the lottery over the actual expected monetary value of the lottery itself. So in this case, it would be greater than. For part C, if u is monotonically increasing and linear, then it would be equal. So in this case, any sort of linear function. You can kind of show this by writing it out. So let's say if our lottery was something like 1/2 x and 1/2 y, then the utility of this lottery would be equal to 1/2 times utility of x plus 1/2 times utility of y. And since we know that u is linear, then we can just apply like the rules for linear functions. So which is equal to u of 1/2 x plus 1/2 y, which this is equal to the u of the EMV of L. So that's kind of showing how they're equal if u is linear. And for part D, it's the opposite of part A, where the function is something like the square root of x. And these functions are more risk averse, so they would always prefer the flat rate amount of money, which is the EMV, compared to actually doing the lottery. So it'd be less than. Okay, so let us work on number 2, which is about MDPs and micro blackjack. So in this situation, we are repeatedly drawing a card that is equally likely to be 2, 3, or 4, and we have two actions. You can either draw, or you can stop if the total score of the cards is less than 6. And if your total score is 6 or higher, then the game ends, and you don't receive any sort of utility. And then when you do stop, and your total score is less than or equal to 5, then you receive the utility of your score, and the game also ends. And when you draw, you receive no utility. And in this case, there is no discount, so we don't have to worry about that. And our goal is to take this problem and formulate it as an MDP, given these 6 states. So first, we want to design a transition and reward function for this MDP. And in the case of transition of, if we start in any state and we go done, and we stop, then we go and done. And this is with a probability of 1 because there is no randomness when we choose to stop. We will always transition to the done state. And this only applies for states in 0, 2, 3, 4, 5. Basically every state except done, because you can't because once you're in the done state, you can't really take any actions because it's a terminal state. And so this covers everything for the action done, or action stop, sorry. And so now for the action draw, which actually has inherent randomness, so we need to consider more values and more combinations. So we can start with, if we are in state 0 and we choose to draw, then I'll write s prime here for now, will be equal to 1/3, because we can go to the states 2, 3, and 4 with equal probability. You can draw like a simple little graph here, where if you choose to draw in state 0, then you either draw a 2, 3, or 4. So you will either transition to a total score of 2, 3, or 4, all with probability 1/3, which is basically described right here. And if you choose to draw in state 1, then you have a similar thing, where you can go to states 3, 4, or 5. Now in state 2, if you draw, then you can either, if you draw a 2, you go to state 4 with probably 1/3. If you draw a 3, then you go to state 5 with probably 1/3. And if you draw a 3, then you go to done, because in this case your total score has exceeded 5 if you draw 4. So it's the same thing as what we had before, and its S prime is in 4, 5, and done. Now for the case of t of 3, and we draw, then we have another situation where we start in state 3, and we can either go to state 5 or done. So if you draw a 2, then you will go to 5. So that happens with a probability of 1/3. But if you draw a 3 or a 4, then in both cases you will exceed a score of 5, so you go to done. So this happens with a probability of 2/3. So we have 1/3 if S prime is equal to 5, and 2/3 if S prime is equal to done. And now if you're in states 4 and 5, then no matter what card you draw, you will always exceed 5. So you will always go to the done state. Oops, this is done, which is equal to the probability. Oops. Which is equal to 1. So these are all of our transition probabilities for every action in state pair. Now for the case of the reward function, I'll make some room over here. Oh yes, I forgot to mention, so for any other state action successor state pair, so otherwise, it's right here. Otherwise, for any other S prime combination that is basically not in this set I have here, you have T of S prime is equal to 0. An example of this is that if you're in state 0, there is no way you're going to end up in state 5 or state 4. Or sorry, so T of 0 draw 5 is equal to 0. Because there isn't a number 5 card that you can draw, so your total score becomes 5 from state 0. Okay, now for the reward function. The only way we can get reward is by stopping. So the reward of S stop, and when you stop you always go to done, so that's always the case, is equal to S, where S is in 0, 2, 3, 4, or 5. And for any other case, otherwise, we have, down with it, we have R of any other combination is equal to 0. So these are the transition and reward functions for this MDP. Okay, so let us move on to number 2, where we want to calculate and apply value iteration to this MDP. And remember that value iteration is a dynamic programming algorithm that is based on the Bellman equations, where the value for time step k plus 1 of S is equal to the maximum over the actions of sum over the successor states of the transition probability times the expected future reward. And in this case, gamma is equal to 1, so we don't have to worry about that. Vk of S prime. So we want to apply this algorithm over and over again for every cell of this graph, or this table. And when we start out, V0, we always initialize all of our values to 0. And to calculate V1, we apply the above formula. So V1 of 0 is equal to the maximum over all actions. So we can do draw first of 1/3 times, we don't get any reward for drawing, plus value at the successor state, which is 2, plus 1/3, 0 plus 0 here, v0 of 3 plus 1/3, 0 plus v0 of 4. And if we stop, we get 0. So this is equal to the max of 0 and 0, which is 0. Now if we do v1 of 2, we get a very similar thing. In the case of draw, if we look at where we never get any reward for actually drawing, and then we also, our value functions for every state is 0. So this for draw will also evaluate to 0. And for stopping, you receive the amount of points of your current state, so you get 2, which is equal to 2. Same thing for v1 of 3, the max of 0 if you draw, and 3 if you stop. So this is 3. And the same thing is for the rest of these. Let me clear up some space here. Okay, so now we're going to calculate v2 for every state. So for v2 of 0, we have the maximum of 1/3 times 0 plus v1 of 2 plus 1/3 times 0 plus v1 of 3 plus v1 of 4. And again, if you stop at this state, you get 0. But now in this case, our values at v1 are non-zero here. So we will actually get a positive result if we calculate this out. So 1/3 times 2 plus 1/3 times 3 plus 1/3 times 4, which in this case times 0 is equal to the maximum of 3 and 0, which is 3, so this is 3. And again, we applied this for 2. So v2 of 2 is equal to the max of 1/3. So you get a reward of 0, and then one successor state will be 4. So you get times 4 plus 1/3 times 5. And then the last one is a terminal state, which is done, which always has. So v of done is always 0, because remember the value function represents the expected future reward, given that you're starting at that state, and then once you're done, the game terminates and you can't get any reward. So that's why it's always 0. And if you stop, then you get 2 points. So in this case, it would be the maximum of 3 and 2, so you get 3. Okay. Now we can calculate v2 of 3. Let me just clear up some space up here. Okay, so v2 of 3 is equal to the max, and if you draw, you get 1/3 times 5, because if you draw 2, then you go to state 5, and then if you draw a 3 or 4, then you terminate, so you get 2/3 times 0, and then max with 3, which is equal to max of 5 over 3 and 3, which is equal to 3 still. And for v2 of 4, no matter what you draw, you will always go to the done, so you get no reward. And if you stop, you get 4 reward, which is equal to 4. And same thing with 5. Max of 0 and 5, which is equal to 5. So these stay the same. Okay, so now to calculate v3, we apply the same ideas. Okay, so v3 of 0 is equal to the max of 1/3 times the value function at 2, which is this, so times 3 plus 1/3 times the value function at 3 from the previous iteration, and then plus 1/3 times the value function at 4, and max with 0 if you stop. This is draw, and which is equal to max of 10/3 and 0. So this will be 10/3. Now v3 of 1, of v3 of 2. Same thing we did before, so 1/3 times the value function at 4, so we get 4, plus 1/3 times 5 with max with 2, which is also still equal to 3. And for the value function at 3, then we have the max of 1/3 times 5 plus 2/3 times 0 with 3, which is equal to 3. And these are the same because if you choose to draw, then you will always get a value of 0. So it's always in the best interest to stop here. Now for the last iteration, so for v4 of 0, we have max of 1/3 times 10/3. Oops, sorry, not 10/3. Times 2 plus 1/3 times 3. Wait, this is, sorry, so it would be v3 of 2 plus 1/3 v3 of 3 plus 1/3 v3 of 4 with 0, which is equal to the max of 3 plus 3 plus 4 times 1/3, which is still equal to 10/3, so this doesn't change. And then if you notice that we're still kind of doing the same calculations, because the calculating the value function at 2, or for this value, we'll be using these values here. And this, we did the exact same calculation in that iteration. So this will still be 3, and then these values only depend on this value, or this value only depends on 4 and 5. Only depends on 4 and 5, which we also did before here. So this will still be 3, and then 4, and then 5. So at this point, if you notice that we have reached convergence because our values at v3 equal the values at v4. So no matter how many more iterations we run of this game, we will always result in the same value functions. Moving on to number 3, we want to extract the policy from this value iteration that we calculated here, or more specifically using these values v4. So if you want to find the optimum policy, we have pi star of s is equal to argmax over the actions of essentially s prime t of s prime r of s prime plus v of s prime. In this case, we'd be using our v4 values to calculate this. So for pi of 0, drag this down a little bit more, pi of 0 is equal to the argmax. So in this case, if you want to keep going, so if you want to draw, then you have 1/3 times, you get no reward, so 0 plus v4 of 2, which is 3, and then plus 1/3 0 plus v4 of 3, which is also 3, and then same thing for v4 of 4. And then if you stop, you get 0. So in this case, it would be the argmax of 10 over 3 and 4, or in 0, sorry. And so in this case, the optimal action is to draw. So in this case, we do draw. Now for pi star of 1, or sorry, pi star of 2, we get argmax of 1/3, and then one successor state. If you draw 2, you go to v4 of 4, which is 4, plus 1/3 v4 of 5, which is 5. And then if you stop, then you get 2. So in this case, it'd be the argmax of 3 and 2. And so the optimal value, or the optimal action, is still to draw. So you draw here. Okay, so now just erase this. Oops, S. So pi star of 3 is the argmax of, so from 3 you can only go to 5 if you draw. So times the value function at 5, and then 2/3 where you're done here. So this is if you draw. And if you don't draw, you get 3. So in this case, it's the argmax of 5 over 3 and 3, which is equal to stop, because this is a higher value than 5 over 3. So we choose to stop in this case. And then now if you think about states 4 and 5, you never want to draw, because no matter what value you draw, you will always go to the done state and then end up with a reward of 0. So you always want to stop here in both these states. We can just do a quick example. Argmax. So with probability of 1, you go to the done state, which has a value of 0. And if you stop, you get, oops, this is a 4. You get 4. So that equals stop. And this is your optimal policy for playing this for the MDP that we described up here, for here. Okay, so now we're taking a look at number 3, which is a question about minimax and expected max. And this is basically presenting a very similar problem, either a minimax game or an expected max game, depending on the question that's going to be asked. So for number 1, it says draw a game tree in which the root node has a larger value if expected max search is used than if minimax is used, or argue why it is not possible. So in this case, we want to find where the root node has expected max larger than minimax, which is definitely very possible because expected max is taking an average over many suboptimal or possibly suboptimal actions. So it is very possible for the root node to be larger for expected max than minimax. An example of a tree would be, imagine if our leaf nodes were 0, 100, 1, and 9. Then our game tree would be like this. So this is expected max. Then this would be 50, this would be 5, and we would have 50 up here. But if this was a minimax tree, then here we would have 0, we would have 1, and then the maximizer would be 1. So as we can 50 is much greater than 1. So this is an example of a tree that satisfies the conditions described in this problem. Look at number 2. It says draw a game tree in which the root node has a larger value if minimax search is used. Oops. If minimax search is used than if expected max is used, or argue why it is not possible. So as I kind of described in the previous question, the expected max will always average over possible suboptimal outcomes and actions. So it is impossible for minimax to have a greater value, because minimax, the minimizer always chooses the lowest possible value. So you can think of it kind of like if you have a minimizer and you have, let's say, x1, x2, which is, these are just like some values. So let's not circle them. Some values. And then, so the minimizer will choose the min of x1, x2. Whereas expect_max, or this expectation node, will choose the average. And it is always true that the min of x1, x2 is less than or equal to 1, the average. So that's why it is not possible. Okay, looking at number 3. Under what assumptions about player 2 should player 1 use minimax search rather than expect_max search to select a move? So player 1 should use minimax if, so P1 should use minimax, assuming that player 2 is playing optimal. In the sense that player 2 is choosing the action that always minimizes the player 1's goal. For number 4, is taking a look at under what assumptions about player 2 should player 1 use expect_max search rather than minimax. So this is another assumption that P1 assumes that basically P2 is playing randomly. You can think of like the random ghost agent in Pac-Man, where it could be like when player 1 applied minimax search, it always assumed like a very pessimistic situation where the random ghost agent always took the optimal move, but in reality it sometimes didn't. So expect_max tries to optimize the expected reward rather than being very pessimistic. So player 1 assumes that player 2 is playing randomly, basically to capitalize on the fact that player 1 or player 2 sometimes chooses a suboptimal move. Now for the last question, 5. Imagine that player 1 wishes to act optimally, and player 1 knows that player 2 also intends to act optimally. However, player 1 also knows that player 2 mistakenly believes that player 1 is moving uniformly at random rather than optimally. So we want to be able to, as player 1, we want to be able to use this knowledge to our advantage of the fact that player 2 thinks that player 1 is a random agent. So for player 1, so we can leverage this information by constructing a game tree in basically player 2's perspective. So player 2 thinks that player 1 is random. So given that player 2 thinks this, player 2 will do expect_max. Or in this case, expect_min, because player 2 is a minimizing agent. So imagine if this was the original game tree. And so on. So since player 2 is acting optimally, since player 2 is acting optimally, but also thinks that player 1 is random, it will replace these maximizer nodes with expectation nodes. And basically find its policy off that. So what player 1 can do is take this game tree and then find basically player 2's policy for every state. So for example, let's say player 2 is a minimizer for this node, and it thinks that given that player 1 is supposedly acting randomly, it will think that maybe this action is the optimal action. Or in this specific state, maybe this action is the optimal action. But basically, what player 1 can do is, for every possible state that the minimizer agent is in, or player 2 is in, it will know what actions player 2 will be in. So now player 1 can construct a game tree like this. And basically, given that it knows, let's say player 2 is going to take this action, it will constrain min's actions to be this action, because it knows for sure that, let's say if player 1 goes left, then player 2 will for sure also go left, because that's what its optimal policy says. So we don't even have to search this entire part of the tree. We don't need to search and we don't need to consider, because we already know what player 2's action will be in that situation. And the same thing for this case. Let's say if it constrains this action, so it constrains this action, so we don't even need to consider this other part of the tree. And basically like this, player 1 can find a way to act more optimally by capitalizing on the fact that player 2 sometimes acts suboptimally.